evaluation of various network structures. So we use some criteria. One is the diameter, which is essentially the max distance. And I write them on the blackboard because otherwise you might not memorize it, these definitions. Then the connectivity. That's the other one. So that's the min number of links to be removed for splitting the network in two. So this is SMS language. The bisection bandwidth. So that is the minimum number of links to split the network into disjoint. Disjoint parts, so the arc connectivity. Then the minimum number of links to be split the network into equal halves. Okay. And the last but not least, the cost. And therefore we took the number of arcs. Right? So we did an exercise on one, and then this completely connected network. So to see what kind of parameters there are for this network, and we came for the diameter, connectivity, and the bisection, and the number of arcs to these kind of equations. So now, don't look at your laptop. We're going to continue this work. So this is an interactive small game. It's nice to see whether you can see the configuration, because then you don't have to learn that by heart if you learn for the exam. Also derive it. And if you say -1 or -2, that's kind of immaterial in the end, right? It's in the order. So I won't punish you for that kind of small mistakes. So the next one, the star network. So what would be the diameter? This is an easy one, right? Yeah. So the number? 2. 2. Yeah. That's the max distance. So the connectivity is easy, right? It's just one node. Bisection is a bit difficult here because it's not a symmetrical network. So you could equally argue that the bisection is 2 or something like that, or that it is 1. And the cost? That's an easy one. P minus 1. Yeah. It's P minus 1 arcs. So that's easy, right? Then the ring. The ring network. So the diameter is simple because it's the half of the ring, right? You can either go this way or the other way around. So it's half, but it's floored, right? Everybody knows what the floor function is. Nobody, everybody knows ceiling and floor functions. No problem. Okay. Also here, the second one, the connectivity. What's the connectivity? 2. Yeah, that's easy. The bisection. 2. Also easy. links. So pretty easy, right? I don't ask you this. This is just in the middle. Very easy cases. 2D mesh. Then the max distance. The mesh contains P processors. Can give an approximate answer. Log P? No. P minus 1 times 2. That's 1. Yeah?
I'm thinking the square root of P minus 1 times 2.
So it's probably close.
Yeah, that was literally
Yeah.
except for the
Yeah.
location.
Because remember that the size is the square root of P processors, right? And you can, the max, you can go either this way or you can go that way. Basically, it's the same distance, right? So, I mean, that can confuse your answer if you don't know, if you think the various path a route can take is different, right? But that's not the case in 2D mesh, right? So now the connectivity. Two? Two. It takes the corner, right? The bisection bandwidth. 4. Yeah, in this case it's 4, but if you have processors, I mean, it can be. It's a square root by square root P by square root P mesh, right?
Radical P.
Square root P. That's true. And then the cost. How many links are there? That's slightly more complicated. But looking at the figure, you should be able to figure that out, right? Anyone has an approximate answer? P? P squared. Plus 1. That's the I missed mine. You said P squared plus 1. Right? Anyone else make a guess? No? Well, let's first give it. That you didn't expect, right? Because what you see is that every processor basically has 4 connections, right? In the middle.
Yeah.
And there are P, and at least for the middle part, that holds for every processor. So that's approximately P. But the directions go both ways, so that it's not 4, but 2 only per processor. Right? So it's bidirectional. So you immediately get this point, but you have to correct for the corners and for these kind of things, and that boils down to the minus P squared. So here you see it's somewhat more complicated, but you can derive it by decomposing in a parameterized way your mesh. That for the interior, you have basically 3 classes. Here is the the inner part, which is regular, right? These is the second one here. And the corner points are even more special. Right? And by summing that up, you come to this conclusion, yes?
Why was there a floor function in the diameter? Because I don't see how this
Well, the floor function is in this case not necessary, but
yeah.
if you have 5 by 5, you need it. If it's let's go.
Oh, yeah. If it's 5 by 5 then square root of 25 would still just be 5. 5 minus 1 is 4. It's integer.
I'm not sure you're right, but I'll look it up again. I'll try to reconstruct it. It's difficult because I'm standing for the board to have an immediate answer at hand. I'm almost sure it's correct. But never mind these floor and ceiling functions, because they basically are exact for these kind of figures, but they do not change the order of things, right? So if you have an order of P, where there's a floor or a ceiling function in there, it's the same order, right? And for me, the order is the most important thing to care about. Right. Hypercubes. This is 3D hypercube. So the diameter we already discussed, right, in the hypercube is log p, and it was one of the nice characteristics of the hypercube, that the maximum distance is always log p. Now what about the connectivity? Should be an easy question also. Also log p. Yeah, you're quite right. Because connectivity is just cutting a corner, right? Because they're all symmetric, and it has log p connections. Right? It grows with log p. Now the bisection bandwidth. It's actually relatively easy to derive if you remember one of the properties of these hypercubes. It doubles, yeah.
2 to the power, the number of dimensions minus 1.
Minus 1, 2 to the power minus, but it's not true. It's p divided by. Why? Because you split the if you double the dimensions, you get another one, and from every point, from every processor in this plane, because the connection to every other processor in the other one, and it regards p divided by 2 processors on each half, right? But the connection goes 2 ways, right? So it's linear in p, right? So that's quite extensive actually, because that means it's a very high bisection bandwidth in this high hypercube structure. The other one, the cost might also be a bit difficult, depending on the order. Give me an order. Not the exact thing. P squared, P log P. P log P? Yeah? Probably right. Yeah. P log P divided by 2. Yeah. Yeah. Because you have P processors and everybody has log P connections, right? But they're going both ways, so you have to divide it again by 2, and then you arrive with this property. also look at cost is the number of arcs, right? So if I have discrete wires, then this would be a suitable argument. This is a little less true if I would make a network on a chip. So then something like the surface of the chip, right, would be a measure of the complexity, of the cost complexity. Suppose we have a two-dimensional chip with the wires laid out like that. Then the bisection bandwidth is supposed to be omega, right? So if I would divide this one in half, I have so many wires going from one end to the other end, right? Then I could say that the cost is lower bounded by the omega squared, right? So omega is then here the minimal dimension. This might be a little bit larger or the same, and then you get this kind of argument is equally valid as a kind of cost function. Right? So it's just to show you an example that cost might be not a real in terms of the number of arcs, might be not in all cases be totally real. And you can extend this argument even for cubes, where you have the wires coming like that, and then it's just the cost is then the square root of lower bounded by the square root of omega times the square root of omega. Get this kind of whatever it's worth for, right? So it's a different flow of arguments. Just to show you that you can also look at it in a different way. Tree network. There, the diameter is also log p. It's actually 2 log p because if you have a tree network, this is a log function. If I want to communicate for this processor with this processor, I have to pass log p switches here and then log p down. So that's to communicate between the two parts of the network. So the diameter is log p. The connectivity is 1 because you just deconnect one node. And the bisection bandwidth is 1, right? Because if you split the network in 2, you always have to go through the top node. So that's a very limiting factor with this kind of tree network structures. The cost is reasonable, p minus 1 runs linear with the cost. So the most advantage you have in this network is that the maximum distance is good, right? The diameter is good. But the bandwidth, the cost is good, but the bandwidth is not good, right? For this kind of network. You can also do the same trick for a dynamic network. I've shown you the omega network, right? So we do the game again. So what is the diameter here? It's a completely different structure, right? So you have to look at things differently. But at the endpoints, there might be processors here or memories, right? But it doesn't change the arguments. So what would be the diameter in terms of p? Right? So we have p endpoints. Right? Here's 8. Here's p is 8. But yeah.
So the number is the same as the number of the layers.
Same as the number of links?
Layers.
Layers, yeah. And that is?
For this case is 3.
Yes. In a generic formula.
Then don't know.
You don't know. So how many many layers? In P.
P minus 1.
P plus 1?
Log P.
It's log P. I mean, because this is a very, very nice network, right? Because you need, if you would need P stages in between, it would be prohibitively expensive to make such a multi-layer network. But if I extend this one, if I have 8 here and I have another 8 here, 16, I have to add only a single layer more. Right? So it's log P. Then the connectivity. You can look at it a bit in a different way here. Anyone? Yeah. P. To connect to.
You would need to basically, between two layers, you need to sever all the links.
No, you just have to isolate in a specific part with a cut. Yeah, 1 or 2 might be more, because you just have to cut 2 to be isolate these 2 nodes, right? So that's, you could argue whether it's 1 or 2. I mean, you could also say, okay, cut here, but that's not very very nice or something. Now the bisection bandwidth. Now you see these crossing of wires, right? What's the bisection? Basically, bisection is easy, right? Because it's splitting the network across these links. So you just have to count the links, which is not easy because they. What do you think? Two log P? Well, let's see. No, it's P divided by 2. Because you have to cut all these things, right? Here. And you have to sum them. Which, yeah,
You can also cut vertically, right?
then you can cut vertically and the network is totally disconnected. If I cut like that, I can do that. You get maybe the same answer, but then the network is completely disconnected, right? I don't have 2 halves anymore, right? But you might end up with the same answer as well. And there's no wonder because I mean there's a fair amount of connectivity in the network, right? So it cannot be log P because that's too low for these intense wires to connect. Well, and the last one is the cost is somewhat more complicated, but that's just P divided by 2 times log P. So that's nice, right? So it's just, this omega network is kind of similar to our hypercube, right? So it has a diameter of log P. It has a reasonable cost function P log P. So in a dynamic sense, this is a very good compromise. Right. Now the question, of course, is in the end, what do we use? Right. Well, that's depending on the stage of technology. I said last week that Intel, at some point in time, I think it was in the 80s of the previous century, had a system on the market called the Intel Hypercube, which was you could buy and had as basic the basic interconnection structure Hypercube infrastructure. They have systems have been built by a company called Connection Machine, which doesn't exist anymore, which was based on a fat tree. Also that has been on the market. But more what you see more in large system is things like systems that are based on toruses, so that are basically 2D meshes with wraparound connections, because they're kind of regular and easy to build, and that also that also is caused by a change of routing technology, and we come to that later. I'll explain. Come back to that. So this is about this part. So the next part we're going to talk about, we're going to build it up, is what is the cost of communication in a parallel system, and can we derive a model for that, right? So then we have to know how we communicate from one point to another point, right? And then after that we're going to continue with the discussion on what kind of communication patterns do we typically see in parallel computers. Is this arbitrary, or are there some standard patterns with on which we can do some calculations on the communication costs? Well, let's start with the cost of message passing. So that's cost of passing a message from one point in the system to another point in the system. What do we have to take into account in at least a reasonable model? Well, the first of all is the startup time, TS. Half of the S is gone here, but there should be an S. Startup time is time to prepare a message, right? So you have your code, it's called send, then it needs to be prepared, the buffers have to be allocated in your system, and the DMA systems have to be prepared for sending the message. And you have to add usually header trailers, so where's the message coming from, where's the message going to, and maybe some error handling things, parity checks or something like that. The second is TH. TH is that if I cannot directly pass the message from with a direct link from the sender to the receiver, I might have to pass other nodes, and these have to hold the whole message or a part of it. And also there it has to store the incoming part into a buffer, and that causes overhead, so that's the whole time. It's basically the latency of the switch involved. And then the other one, the last one, is the time it takes for a word to transfer between two nodes. And TW is 1 over R, which R is the words per seconds I can transfer over the channel. I do not specify how large the word is, because that is technology dependent. Can be 1 bit, can be 60 bit. It's immaterial, right? It's TW is the time it takes for a word to be transferred from 2 points, right? So that's a simple model. Now the first method is a simple method where we have a message of size m words, and the number of links is L, right, in this case. The message starts from the point with indicating the bar here. This is the message, and it has to be transferred from here to here, right? So basically what you do is that the whole message is transferred from one node to the other until it ends at the other node. And that's what we call store and forward. Now the communication time in this simple model we have can be modeled like this. It's very strange, because I'm almost sure I used a different font type, then is appearing on my screen now. That's probably because this system is not capable of translating the right font size. The communication time is the startup time plus the number of words plus the time to transfer one word plus the whole time times the number of links I have to pass. Right? Because every time I have to pass m times TW words from one place to the other place. Right? Yeah, do we see that? So this is a simple one. That is strange. No, it's the same. Is it this? No, it's a different font, right?
Yeah, it's different.
Curious. I can simplify this mod. Sometimes I can simplify this formula. For instance, if I think that the whole time is neglectable, legible, right? Then I can simplify by removing this term, and then the formula becomes simple: TS plus ML times TW. Right. Now, a different method would be to not transfer the whole message, but do a kind of packet routing, where the message is again n words. We have number of links is L, but we split the message in R packets. And to every assemble of a packet, there is some overhead associated. And let's call that S, say 110%, right, or something like that. So we have to take into account the time to make the packet and the time to transfer the packet. Now, how does this work? With a simple system, we have a message. We split it in the most basic case in 2 packets. And then we send the package one after the other in a kind of string to the other side. Right? That is the idea about packet routing. So I split it and I start the first half, and then after the first half has been sent and received and been forwarded to the next one, I can put the other one. Then our formula becomes exactly the same, but this one becomes somewhat more complicated. That the transfer time of word is made up by the time to make the packets plus the time to transfer the packets plus the overhead factor of the packets. Right, so somewhat more refined. Now, if I make the amount of packets very large compared to the message, then I get a different picture. And if I assume the overhead of packet can be neglected, because yeah.
So that means that packet overhead is not dependent on the number of packets.
No.
It's a one-time overhead.
It's a one-time overhead, and because we're dealing with many things, I can kind of neglect it, right? And what you see then is what you in this method do is first establish a route. So you want to transfer the message from this point to this point, and I reserve the route in advance, because otherwise I get too much overhead, right? Because and then I stream the packets over that route to the other way. Yeah, yeah.
When you reserve the route, isn't it any time delay for that?
Sure, sure. But if the message is large enough, I mean, we're talking about order analysis, then it's neglectable, right? Then your message time may take 100 seconds, and the time to reserve the route is only half a second or something like that, right? So, because otherwise, if that's not the case, it's not worth doing. So let's cut through routing And what we get for our formula then is that, essentially, the communication time is the startup time plus the time to transfer a word plus the whole time per number of links. And this is really different than, it is as if, apart from this overhead, it is as if I have a direct connection between the 2 points. Right? Yeah?
Can you please explain again what is time for?
The whole time is to be able, the packet comes in, I have to store it in an internal buffer for I can send it to the next one, right? But if it makes a big difference if it's a small packet or a large message, right? Because if it's a small packet, I only need a few buffer spaces to do that, and I can let the hardware do it, and it's way faster to do these transfers. And in time of the total transfer, it becomes a bit unnoticeable, this whole time.
So it's the processing of the header where the message is out, right?
Yes. Yeah, and the processing of the header and the storage of the intermediate storage of the small packet. If I, again, say this is insignificant compared to the rest, then I have that the communication time is the startup time, which is usually somewhat more significant, and the message, the word transfer time. So there we have now 2 different models. There's one consequence that this cut-through routing only works when the messages are relatively large, because otherwise you get these effects of packetizing